All right, so when we have this initial velocity that has an x component and a y component, the x component is adjacent, and that is the cosine function. So the cosine of theta would be adjacent v naught x over hypotenuse v naught. Multiply by v naught on both sides. Do we get that the initial velocity in the x direction would be the initial velocity times the cosine of the angle? Now in the y direction, the y component is opposite of the angle. Okay, and opposite goes with sine. So the sine of the angle would be opposite v naught y over hypotenuse v naught. Solving for v naught y, so our initial velocity in the y direction would be v naught sine theta. And this is where you can see if your angle is bigger, the sine of a bigger angle, the sine of theta goes from 0 to 1 as theta goes from 0 to 90. So we get a bigger and bigger component of the velocity as the angle increases. And the opposite happens for the x direction. You get a smaller and smaller component. So imagine if you could raise this arrow up. So if I could raise this arrow right here for my velocity, if I raise it up, see how the blue arrow would get longer and the red arrow would get shorter? The height gets greater, but the base gets smaller. So that's how those are related. Okay, so in our discussion yesterday, we decided that the all the forces, the free body diagram, FBD, for the object that was projected. In our discussion yesterday, it was the basketball, projectile, whatever it was, but the only thing acting on it once it leaves the projecting apparatus, so once the basketball leaves your hands, once the projectile leaves the projectile launcher cannon, whatever, the gravitational force is the only thing acting on it, and it's unbalanced. We've sucked all the air out of the room. Okay, so the only acceleration we have is a vertical acceleration. There are no forces in the x direction. There are no unbalanced forces in the x direction. The acceleration in the x direction is 0. Unless you've got rocket boosters attached to this projectile, then it's not a projectile really anymore. Or you have fairy wings, or you put some pixie dust on it or something like that. So if there's no acceleration in the x direction, every moment it's in flight, it's moving with the same velocity. So I'm going to draw the same velocity arrows at every place. So the velocity in the x direction is the same no matter where you are along the path, because the acceleration in the x direction is 0. There's no net force in the x direction on our little free body diagram. Now what's happening in the y direction? Is there an acceleration in the y direction? Yes. So what's going to happen to our velocity vector? Is it going to increase or decrease as we reach the highest point? Shouldn't it decrease to where it's what at the very top? Yeah, the velocity in the y direction is 0 at the maximum height. Then what's it do? It stops because the acceleration due to gravity is causing the velocity to decrease till it stops, and then comes back down. So what's the direction of the velocity at this point right here? Negative and a little bit, maybe equal and opposite to that one if those are the same heights. And then when it hits the ground, same as the initial velocity in the y direction. So the final velocity in the y direction is equal and opposite to the initial velocity in the y direction. So when it hits the ground, if this is a ground-to-ground launch, then the velocity or the speed that it hits the ground with was the same speed as it took off. And it's going to hit at the same angle that it took off at. So that's a great little bit of information for a ground-to-ground launch.